Hello everyone, I am Anto Lonappan from University of California, San Diego. First, I would like to thank the organizers of parity-violation from home for inviting me to speak here. Here I will be presenting my recent two works together, titled Cosmic Birefringence Constraints on Anisotropic Birefringence and the Future Improvements. Here is a quick outline of what I will cover in this talk. I will start with a brief overview of cosmic birefringence, then discuss why it matters in the broader context of cosmology and parity violation. Next, I will go through the constraints on the anisotropic cosmic birefringence inferred from the CMB B-mode polarization data. Finally, I will describe how we can improve these constraints through delensing and what that means for the future experiments. Let's talk about what cosmic birefringence actually is. The figure shows the journey of CMB photons from the large scattering surface all the way to our detectors. As these photons travel through the universe, their polarization angle can get rotated. That's what we call birefringence. Uh, Along their path, the signal also passes through foregrounds such as galactic dust emission. Finally, when the signal reaches our instruments, any small polarization angle miscalibration in the detector can also rotate the polarization we measure. So, what we actually observe is a combination of rotation angle, which we denote here as alpha plus beta. So here alpha represents the instrumental miscalibration angle, while beta represents the cosmic birefringence, the part of cosmological origin that we are truly interested in. Now, beta itself can be of two types. It can be isotropic, meaning same rotation across the entire sky, or anisotropic, where the rotation varies from one direction to another. And both probe new physics. Uh, Now, let's talk about what kind of new physics cosmic birefringence can probe. So here is the relevant Lagrangian that describes the interaction between a scalar field and electromagnetic field. When the pseudoscalar field couples to photons through Chern-Simons term, we can generate a cosmic birefringence signal. So under standard Maxwellian electromagnetism, this effect should be zero. So if we detect any non-zero rotation, it would point to new physics beyond the standard model. So for ultralight scalar fields, this coupling predicts a rotation angle proportional to the distance the photon travels. And this kind of couplings could be connected to axions or axion-like particles, possible dark matter candidates, or even the dark energy field driving the cosmic acceleration. So what does this do to the polarization? Here we start with the E-mode polarization. So with such coupling, this E-mode polarization get rotated into B modes, creating a parity violating signal in the CMB polarization. Now that I have covered the small intro, I will move on to the results from our first study, where we used the CMB B-mode polarization data to place constraints on anisotropic cosmic birefringence. Following Namikawa 2024, where he derives the exact expression for the B-mode power spectra that arises from the anisotropic birefringence, here the equation for CLBB shows how mode coupling occurs between E and B modes when parity symmetry is broken. This component here is the direct result of parity symmetry, showing the anisotropic rotation mixes E and B modes in a way that couldn't appear in a parity conserving universe. The last term in the expression receives its contributions from the power spectra of the anisotropic birefringence field. We assume this field follows a scale invariant spectra, uh, which we can conveniently parameterize with an amplitude ACB. Finally, this connect back to the massless pseudoscalar field, which act as a source of the anisotropic cosmic birefringence responsible for this B-modes. So now that we have the B-mode spectra predicted from anisotropic cosmic birefringence, the green line here shows that the contribution for an amplitude of 10 to the power minus 4 radian square. For comparison, I have shown other B-mode components, the tensor modes in blue, the lensing contribution in orange, and an anisotropic component corresponding to rotation of about zero point 0.6 degrees. So in this work, we combine CMB B-mode data from multiple experiments, BICEP, POLARBEAR, SPT, and the most recent ACT data to place the constraints on the anisotropic birefringence amplitude parameter ACB. So to extract the amplitude of anisotropic birefringence from data, we build a joint likelihood over all B-mode data sets. The expression shown here represents the log likelihood function, where we compare the observed band power to the theoretical model prediction. And each band power is modeled as a combination of several components: the tensor contribution scaled by the tensor to scalar ratio R, the lensing term scaled by the amplitude A lens, and then the anisotropic birefringence term proportional to ACB. We also include contributions from isotropic birefringence and foregrounds to make sure all relevant sources of B modes are properly accounted for inside inside the theory. So here is the posterior probability of ACB for different data set combinations. So SPT alone shows about a 2 sigma preference for a non-zero anisotropic birefringence, consistent with the result reported in Toshia's paper. However, we combine all data sets, BICEP, POLARBEAR, SPT, and ACT. The results remain consistent with a zero amplitude, indicating no strong detection yet. Um, for the likelihood analysis, we obtain the best fit value for the anisotropic birefringence amplitude, which is the ACB, or 0.442 times 10 to the power minus 4. So with 1 sigma error consistent with 0. Without SPT, this reduces to like a 95% upper limit of ACB 10 to the power minus 4. In the left plot, I show two sets of results. So one considering anisotropic birefringence alone, and the other where both isotropic and anisotropic components are fitted simultaneously. So which shows the degeneracy in the parameter. Um, so far, I have shown how the current constraint on anisotropic birefringence from the existing B-mode data. The next question is how can we improve these constraints further? So in the next few slides, I will show how delensing can enhance our sensitivity and what kind of improvements we can expect from both isotropic and anisotropic cosmic birefringence. So delensing is typically used to improve the sensitivity to tensor to scalar ratio R. But here, I am applying it to improve the constraints on cosmic birefringence. As CMB photons travels towards us, their E modes polarization can be lensed to B modes by weak gravitational lensing from the large scale structure. So this E to B conversion is parity conserving. So it doesn't mimic the parity violating signal we are searching for. So in the left plot, I show the B-mode power spectra from different sources, the lensing contribution, the isotropic birefringence, and the tensor component characterized by R. So how is the delensing actually done? So one method works as follows. We start with the E-mode map and the lensing potential or the deflection field. By combining these two, or properly saying convolving, so we can generate a B-mode template. This represents the portion of the observed B-modes that's coming from the lensing. So we then subtract this template from the B-mode measured B-mode map, and the result is a residual B-mode map, which with much lesser lensing power, which makes it easier to detect any small birefringence induced signal that may be hiding underneath. So in this slide, I am showing the EB spectra for the isotropic birefringence case, uh, both before and after delensing. The, the blue error bars corresponds to the lens spectra, while the red error bars represents the delens case. So you can see that delensing leads to a reduction in variance. Um, So here I show the impact of delensing on improving constraints on the isotropic birefringence angle, so separated by the multiple range. On the left, I focus on the large scales, multiples below L equal to 200. On the right, we extend the analysis to include higher multiples up to L equal to 1000. So the plot shows results for three experimental noise levels: 6 microkelvin arc minute, achievable by the Simons Observatory nominal configuration, 2 microkelvin arc minute corresponding to LiteBIRD, and 1 microkelvin arc minute, which is representative of an XO extended or a CMB S4 like sensitivity. Uh, the blue error bars corresponds to the lens case. The green shows the delensing using a quadratic estimator of the deflection field. And the red represents the iterative delensing, which achieves the best residual cleaning. So here are the main takes. Here, so the main takeaways are the Simons Observatory can gain roughly a 10% improvement in the sensitivity to isotropic birefringence through delensing. And lower noise experiments can benefit by about 30% with simple quadratic delensing, quadratic estimator based delensing, and up to 40% with iterative delensing. So, and both large scales and small scales, delensing contribute significantly. So, comparing them will be crucial for the future CMB experiments. So, let's talk about the delensing bias, which is a very crucial part of the final inference. So, what is it? So, when we delens the B modes using a reconstructed lensing potential, there can be spurious correlations between the B-mode map and the estimated potential. So these artificial correlations can introduce a bias in the delens spectra, which is not, uh, if not corrected, can lead to a wrong inference. So here I have tested two delensing strategies and compared them with an ideal case. So in strategy one, we use the reconstructed potential over the multiple range 200 to 4000 to build the delensing template. And we remove only the B mode multiples below L equal to 200. So this avoids overlapping modes between the reconstruction and the delensing operation. So in strategy two, We estimate the bias in a delens spectra using a Gaussian simulation where there is no real lensing is there, and then subtract that bias similar to what a Planck analysis did. So in the ideal case, I combine the Gaussian N0 noise with the true potential and used it for the delensing. So it represents the theoretical best scenario without reconstruction uncertainty. So on the right-hand side, I show the posterior distribution of the inferred isotropic birefringence angle for 6 microkelvin arc 6 microkelvin arc minute noise level. So the takeaway messages are: so if we don't handle the delensing bias properly, we infer a wrong isotropic angle, um, as shown by the orange curve. The strategy one achieves about like 10% improvement while avoiding the spurious bias. Strategy two, which mimics the Planck-like approach, actually gives a larger but incorrect improvement, even outperforming the ideal case. So showing that this method is not optimal for low noise experiments. So now let's see how delensing can help improve the anisotropic birefringence measurements. So just like the lensing potential, we can estimate the anisotropic birefringence angle using a quadratic estimator and then compute its power spectra CL alpha alpha. This estimator, similar to the lensing case, is affected by several bias terms, including N0 and N1. But for particular this case, most importantly, the lensing bias. So in this plot, I show the anisotropic power spectra obtained from the quadratic estimator applied to both lensed and delensed CMB polarization data. So the blue error bars corresponds to the lens case, and the green error bar shows the delens case. So the dashed lines indicate the N0 bias for each case respectively. Um, in the bottom panel, I show the ratio of the total bias to the signal, which clearly gives a comparison of how much delensing reduces the bias. So how exactly delensing uh, improves the anisotropic estimate. So first, it lowers the N0 bias, which comes from Gaussian noise in the estimator, as you can see here, comparing these two lines. Um, uh, and more importantly, it tremendously reduces the lensing bias. So as you can see, this blue line compared with the green line here. So this means delensing not only helps the isotropic angle measurement, but also makes a significant improvement in reconstructing the anisotropic birefringence power spectra. So similar to the isotropic case, delensing bias is also very crucial in the anisotropic birefringence analysis. In this plot, the green curve shows the bias in the inferred amplitude that arises from the delensing bias itself. The blue curve represents the lens case, and the orange curve corresponds to the unbiased case, which leads to a significant improvement of 30% for a 1 microkelvin noise level measurements. So to summarize, anisotropic birefringence induces a distinct B-mode signal in the CMB polarization. Using recent B-mode data, we have placed an upper limit of 10 to the power minus 4 radian square, with all current observed with all current observation, B-mode observations, and this is still consistent with no detection. In another paper, we show that delensing plays a major role in the improving these constraints. It significantly enhances our sensitivity to both isotropic and anisotropic rotation angles by removing the lensing-induced variance and lowering estimator biases. That's it, and thank you very much for